Good evening, everyone. On the behalf of Department of Mathematics, Wilson College Autonomous Mumbai, I welcome you all in the today's session. Our today's guest is Gaurav Sawant sir. He is an assistant professor at Department of Mathematics, Veermata Jijabai Technological Institute, Vijayati, Mumbai. He will deal with the topic of ordinary differential equations today. Over to you, sir.
Okay. Uh, Thank you, Prakash, sir, for the kind introduction. So let's begin. So in the last session, yesterday's session, we covered until orthogonal trajectories, right? We did some simple differential equations. We did separable, and we like ended with orthogonal trajectories. So today we will look at these three topics: homogeneous differential equations, exact equations, and integrating factors together. And if time permits, we can do some additional topics. All right. So first thing, recall that we had our first degree or first order ordinary differential equation as dy by dx equal to fxy, right? So it is called homogeneous. So this is homogeneous of degree n if the function f satisfies this following scaling property: dx dy equal to t power n fx. And when this happens, I can make a simple substitution. Z equal to y by x, and also the related z plus x, z over dx equal to dy by dx. To simplify this further and hopefully get into a separable form. All right. Then sometimes the one is able to split this fxy into a numerator by denominator form, and then the first order differential equation can also be written in the form mxy, let's say dx plus n xy dy equal to 0. Okay, there can be cases where you could have something on the right, but we will not worry about those cases at this time. And so what happens is that you have to observe this. So if it happens so that the partial derivative, which sometimes I will write in the partial derivative notation, sometimes I will write in the subscript notation. Is there any question? So if these functions m and n satisfy this partial derivative equality, then this equation is called exact. The reason is that if this thing happens, then there would, if so, then there exists some function capital F x y such that this time let me write the subscript notation fx equal to m and y equal to n. So this function f will have to be like twice continuously differentiable in both the variables x and y. So essentially, the above equality of partial derivatives simply follows from the independence of order in second derivative. So this thing is actually the same as fxy equal to fy. Okay. So when such thing happens, if we are able to confirm that these partial derivatives are equal, then we can choose one of m and n. We integrate with respect to the corresponding variable. So for instance, so to solve, find either integral m with respect to x dx, which should be a function, uh, let's say, let me write g1 uh, xy plus some function of y, because here the variable which we are integrating with respect to is x, and then the constant term may possibly have a dependence with respect to the other variable or variable. So here there is the other variable is y. So you could have this thing and then differentiate the right hand side with respect to y, and you would get uh, del g1 by del y plus phi 1 dash y, right? But then that particular quantity needs to be equal to like this n. So you essentially will solve this, and then you will probably get a much easier expression to find this psi1y. And once you get that, you are done. So the solution will be of the form fxy equal to constant. So this integral m dx is a candidate for this capital F. And the same thing can be done the other way also. So then also find integral n dy, it would be some g2x y plus phi 2 of x. And then you differentiate with respect to x and then solve del g2 over del x plus phi 2 dash x equal to m. And then find phi 2. And once that is done, you can simply plug it back in and obtain your solution in this form. So this is fine so far.
Yes, sir.
Then let me add a page. Yeah. Most of the time, what will happen is that you can write like separate this thing out in the form m dx plus n dy equal to 0. But this may or may not be exact. So no, I will just write not exact for the time being, which just means that m y is not equal to nx. Okay. So in this case, our like previous method does not work. But what works is if we multiply throughout by a suitable function mu, then this equation may become exact. So an integrating factor is a function mu, which is typically involving both the variable, or it can involve only one of them. It could be a constant with respect to like, but it will typically have two variables such that mu m dx plus mu n dy equal to 0 is exact. So depending on the form of m and n, there are several different approaches to finding this integrating factor. So, well, if this expression has to be exact, then the first thing that we must have is the cross partial derivatives are equal. So del mu m or del y needs to be equal to del mu n over del x. Okay, and we can simplify this further to obtain 1 over mu. Yes, anyone has a question or
Uh,
anyone
uh,
have?
no, no, sir. Please continue.
Yeah, yeah. So 1 over mu uh, n del mu over del x minus m del mu del y equal to del m del y minus del n del x. So typically this integrating factor will always have this expression. So let me just put a highlight underline to this for the time being. Okay. So there are some special cases. So if mu is a function of x alone, if that happens, then this del mu by del y term will not appear, and you will be reduced to the problem 1 over mu n d mu by dx equal to del m del y minus del n over del x. So what you do is you take, let me just take this here, del x equal to 1 over n, this. And let us call this right hand side expression as, let's say, some g of it. Okay. So it has to be like it is going to be treated as a function of x. Okay. Then and then this if it is a function of x alone, then this partial derivative actually becomes a full derivative, and now it is in a separable form. You get d mu over mu equal to gx dx, and which after a few steps you will have mu equal to exponential integral gx dx. Okay. The same way, if mu is a function of y alone, then a similar reasoning works. This partial derivative with respect to x will vanish. You will be left with minus m del mu by del y, but that becomes d mu by dy. And after a few steps, you would get some form mu equal to e power integral minus some h y dy. Or like the way you would change this, this will be minus over 1 over m del m by del y minus del n by del x. That will be the function h of y. And then you will have this kind of form. That minus can come out, that is fine. And there are some other forms which can also be used. So, for instance, let us look at, you could have certain expressions that you can use. So, for instance, if mu is a function of, let's say, x over y or y over x, let's say of x over y. So, there is like many books will give a certain table, and what you will have to do is look at this highlight underlined expression and see whether you can extract a suitable form of the function. So let me make this as a table below. Uh, Here is the function of, and then uh, form of differential. Okay, so I would have, if it is a function of, let's say, x over y, then one looks at the differential as y dx minus x dy over y square. So if you are able to write the right hand side expression, the expression in the brackets, somehow in the form y dx minus x dy over y square type, then you make a change of variable x by y is equal to z, and then appropriately change variables, convert it in this form, and then proceed. So in that case, that mu will be a function of that x over y or whatever that other variable is, and then one can make further simplifications. So let me add another page. Yes, here's a function like this. If it is a function of xy, the here, the corresponding form is dx. It's simply x dy plus y dx. You could have uh, uh, other like relations as well. If it is a function of x square plus y square, in that case, I will have the formulation x square plus y square equal to twice of x dx plus y. There are several other formulations which I will not mention for the sake of time, but you can look them up and work with. Okay. So there are cases where certain problems can be solved through homogeneous equation methods. Certain things are exact, certain things are not exact, and in this case, you will have to go through integrating factor and so on. And you will actually need to observe and just realize which form is the right one. So there are cases where you can, like some questions can be solved easily through homogeneous. Many of the times they may be exact, and the exact differential equation method might be faster. Depending on that, one can solve different kind of problems. So let's start with our first problem of the day. All right. So now this particular equation, y minus x dx plus x plus y dy equal to 0. This can be converted into our familiar looking form, uh, dy by dx equal to x minus y over x plus y. Okay, so I wrote it in the form dy by dx equal to fxy for this particular instance. So if I scale x and y by the same factor t, if I like replace x by tx and y by ty, the resulting function is well it will just be the same. So if this is fxy, observe that f of tx ty is actually equal to fxy. So this is homogeneous of degree 0. Okay, so t power 0 fxy. So this is homogeneous. So you could try a substitution. Z is equal to y by x, and also have the differential formula dy by dx is equal to z plus x dz by dx. Okay, so let's do these substitutions here. So on one hand, I have dy by dx as this expression. So let me write that z plus x dz by dx equal to, on the right hand side, I can divide through the numerator and denominator by x, and have 1 minus y by x over 1 plus y by x, which happens to be equal to 1 minus z over 1 plus z. Right? And then I just subtract z from both sides, and I will have x dz dx equal to, so 1 minus z minus 2z minus z square over 1 plus z. Okay, and then this becomes 1 plus z over 1 minus 2z minus z square dz equal to dx over x. Right?
Yes, sir.
Is everyone okay with this?
Yes, yes.
Yes. So now you will have to make an appropriate substitution here, and then go about. But as you can see, it is essentially taking much longer, right?
Yes, because the form left hand side, it would require some certain type of substitution.
Yes. So you'd perhaps have to do another substitution, and
Yeah.
so I will just write longer for the time being. But
Yes,
what
yes.
one can do is observe that the same equation, y minus x dx plus x plus y dy. So let
Yes.
me let me
It is
attempt this in the exact form. So y minus x dx plus x plus y dy equal to 0. So
just
if I
just
look at
leave. Uh,
this and put m and n, and then I actually see that the partial derivative of m with respect to y is equal to 1, and it turns out to be the partial derivative of this n with respect to x as well. So this makes this exact. Okay, and the moment it has become exact, now I can let's say take up this m function, integrate with respect to x. So I would have, let's say, f xy, which is the expected solution, equal to integral m dx, uh, which turns out to be equal to integral y minus x dx, that is xy minus x square over 2, and you will perhaps have a function of y as a integration constant of integration with respect to x. All right.
yes, sir.
So now taking this as a candidate, I so equate f sub y equal to n, right? So on the right hand side, that f sub y, I am going to have x, then that minus x square by 2 will just go away, and I will have phi dash of y, that is my f sub y, and on the other side I have n sub x. So on the other hand, I have n that is equal to x plus y. So which gives me phi dash of y is equal to y, which readily gives me phi of y equal to y square over 2 plus c. Okay. And once that is done, all that is required, I just substitute this phi y upstairs, and I will have f x y equal to xy minus x square over 2 plus y square over 2 plus c. And anyway, the solution of this is f of xy equal to a constant. So that constant can be absorbed, and it will be some other constant. So I'm writing it as a capital C. So this should be the answer for that question. So given that there is an initial condition y of 0 is equal to 1, use initial condition y of 0 is equal to 1. Okay, so we put x equal to 0, y equal to 1. So the moment we do that, the first two terms drop out. The third term is y square by 2, that is half, and that is equal to the constant c. So this capital C is equal to half, and which gives us the solution as fxy as xy minus x square over 2 plus y square over 2 equal to half. Okay. Now we only have to check the given options and see which point is there. So I will write those options for you here. So the A option was 1 minus 2. B option was 2 minus 1. C was 2, 1. And D was minus 1, 2. Okay. So the question was which of these points lies on the curve, or which is part of the solution. So you have to substitute x equal to the first number, y equal to the second number, and see what happens.
Sir, option C is, I think, the answer.
Okay, so let's check. What happens in the case of option A is that 1 times minus 2 minus half plus 2. So let's write it. So A will be minus 2 minus 1 by 2 plus 4 by 2. So this is equal to minus half. So that is definitely not equal to half. So option A is not right. If we look at option B, I have 2 and minus 1. So minus 2, then minus x square by 2. So minus 4 by 2, and then plus half equal to half. And this also doesn't work. So because this is minus 7 by 2, which is not equal to half. So option B will also not work. For option C, I will have 2 minus x square by 2, so minus 4 by 2 plus y square by 2. So this actually turns out to be half, and therefore this is the correct option. And this being only one answer correct type question, it this being an MCQ, you are done. Okay.
Okay, sir, one question.
Yes.
The Fy, the previous page, Fy, yes, yes, equate Fy is equal to N. Here, what is
Yes.
done here?
Yes. So the thing is that let me go a little more before, where I talked about
Yes, yes,
exactness. So
okay.
the idea is that you are expecting a solution of this form, f of xy is equal to constant.
Yes.
So if you take the total derivative on both sides,
Mm,
I will have, so let's write that total derivative in blue somewhere here, where is it? So let me write it here. So del f by del x dx plus del f by del y dy equal to 0 is what we will get.
yes.
So if you see, if the function m is exactly satisfying this f sub x, or this del f by del x equal to m, and fy equal to n will correspond to this del f by del y equal to n. So in case your functions m and n are able to uh, like are of this form, then this works, because when you take the mixed partial derivatives in different orders, they have to be the same. That is correct. Okay.
Mm,
Where did my pointer go? Okay. Yeah, for some
okay.
reason my pointer is, yeah. See, this specific equation tells you that the mixed when you take mixed partial derivatives, the order doesn't matter. So when I take the partial derivative of m with respect to y and of n with respect to x, I should get the same thing.
Yes,
And
sir.
that is exactly where the exactness started. Once that happens, then you can just do the respective integration and thereby get the answer.
Okay, okay, sir, got it.
Yes. Okay. Okay. So we got through this. So let's move on and look at yet another question. So I have mentioned these three things together because many a times you will see that there can be a mixed question asked, in the sense that you could have like multiple concepts being asked in the same question. So the following that I'm going to show you is one such instance which came in the 2024 exam. So let me just scale it up for you. For some reason, I find it. Yes. Okay. So now I have an expression which looks like this. And there are a bunch of things. It talks about homogeneous equations. It talks about exact equations. It talks about integrating factor, right? So there are a bunch of things that are happening. So let's just break this question down in simpler form. Let me add a page and come back. Yes. Okay. So let's write this in the form m dx plus n dy equal to 0. So my m xy is equal to, I will just open it up, 8xy minus 9y square, and nxy is equal to 2x square minus 6xy. Okay. And since m is associated with dx and n is associated with dy, we just check for cross derivatives. So we check my. So if I take the y derivative, I will get 8x minus 18x square, 18y, and nx, I'm going to get 4x minus 6y. So definitely these two are not equal. So this tells you that this is not exact, right?
Yes.
So therefore, option B is already out, correct? Then
Yes.
let's change this up. Let me write this in the form dy by dx equal to fxy. So if I do that, I will have dy by dx equal to 8xy minus 9y square divided by 6xy minus 2x square. Okay. So now this is my fxy, the right hand side expression. Okay. And then I see that the total degree, like involving both x and y together, is 2, both for numerator and denominator. And there is no like degree 1 or a constant term appearing. So this actually will automatically be a homogeneous equation. So since f x dy equal to fxy, this is homogeneous. Okay, but then the say D option claims that this equation is not homogeneous, but we all actually saw that it is homogeneous. So this option also goes out of the path. Now, if you look at the remaining two options, non-exactness was already mentioned, but it just asks whether x square is an integrating factor or not. Okay, so our matters are actually much simple. So we simply multiply both m and n by x square and see what happens. Okay, so I will have x square m equal to 8x cube y plus minus 9x square y square and x square n equal to 2x power 4 minus 6x cube y. Okay. And now of these new functions, you take the cross derivative. So uh, x square m partial derivative with respect to y equal to. So when I take this, I will have 8x cube minus 18 x square y, right? And on the other hand, I will have x square n x is equal to 2x power 4, so 8x cube minus 6x cube y minus 18 x square y. So you see that both the sides are equal. And integrating factor is a function which on multiplying throughout makes the given non-exact differential equation into an exact one. So therefore, x square is indeed an integrating factor. So this is correct and this is correct. All right, simple enough.
Yes, sir.
Yes, sir.
Yes.
Okay. Okay. Let's go ahead and look at something else. So there are a bunch of problems. I want to pick one. So yeah. Okay, let's look at some exact equations that will actually be a different kind of fun. Let's see. All right. So our equation is of this form: 1 plus x square y cube plus alpha x square y square dx plus 2 plus x cube y square plus x cube y dy equal to 0. So there will there are always these kind of questions coming in the uh, actual paper, which will just ask for the a certain constant or something. So let's just quickly solve it. My m is 1 plus x square y cube plus alpha x square y square. My n is 2 plus x cube y square minus x cube y. Okay. I will have my equal to 3x square y square plus 2 alpha x square y nx equal to 3x square y square minus 3x square y. Okay. And well, this is supposed to be exact. So both these sides have to be equal. And then one can readily infer that 2 alpha is equal to minus 3, alpha equal to minus 3 by 2. But there is no option.
এটা
What
এটা
happened?
সুর এটা সুরকি ওঠার মতন, এই যে এটা 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 সুরকি ওঠা, এটা বাদ দিয়ে বাকি সব আর গন্ধটাও খারাপ হাজার মতন, শুধু ওইটুকু গোটা পায়ে করে।
Yes. কি হলো?
ও
Please.
সরি 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 স্যার, বাই চান্স স্যার।
Yeah, yeah. Okay, so turns out either I have made a typo while transcribing the question, or there is something else going on. Oh, my typo is here. So it is correct. So 2 alpha is equal to 3 and alpha equal to 3 by 2. So this happens to be the correct answer. Yeah. All right. So this is pretty exciting. Let's try to look at another problem which will have some extra things going on. Okay, so let's look at this particular question. All right. So this time the particular constant that we have to evaluate is appearing in both sides. Just the same drill. Plus n square x square y a equal to small n x cube plus 3x square my equal to 6xy plus n square x square nx equal to 3nx square uh, plus 6xy. Right. So we got n square x square equal to 3nx square. N square is equal to 3n, which gives you two answers, n equal to 0, n equal to 3. And since the question asks for non-zero value, my answer is 3. Right?
Yes, sir.
Then there are some kind of situations where you would be given the question in a different form. So let's look at one multiple choice question, and later on we will also have a NAT type question. So let's do this. A bit press to get a new page. Okay, so this time this expression is given in a different form, as an in an operator kind of form. Okay, it doesn't matter. We just want something times dx plus something times dy type. Okay, so let's handle this question. So we have m equal to y minus y square, n equal to x. So there is really nothing big happening, but you can already clearly see that this is not an exact differential equation. So I will, because my is 1 minus 2y and nx is equal to 1. So clearly these are not equal. But then the question is talking about integrating factors, and it has already provided a candidate function 1 over x square y square to work with. So let us look at this. So f times m is equal to y minus y square over x square y square, which let me take away one of the y's, 1 minus y over x square y. And fn is equal to 1 over xy square. Right. So now let us take the cross derivatives and see what happens. So if I do fm y, I should have x square y minus 1 minus y x square divided by x square y square. So what is this equal to? Minus x square y minus x square plus x square y divided by x4 y square, and then the x square y terms cancel, and I will be left with minus 1 over x square y square. Correct. On the other hand, if I do fn x, I would similarly get so there is just 1 over y square, right? So 1 over y square will be treated as a constant, and then minus 1 over x square, which is minus 1 over x square y. So as you can see, these two are equal. So this particular function is indeed an integrating factor. So already of these options, option D gets out, right? So now that we have obtained an exact form, Fm in this form. So let's rewrite the differential equation just for simplicity. So I would have Fm dx plus Fn dy equal to 0, and which as we had obtained 1 minus y x square y dx plus x y dy equal to 0. So this time, let me focus on this time. Let me use the function n, integrate with respect to y, and then later on take the derivative with respect to x and equate it with the m function. So the candidate capital F x y would be uh, integral n fn dy. So we'll have to, the candidate is fn dy, that is dy, that becomes minus 1 over xy plus some function of x alone, right? And then m should be equal to fx, which leads us to 1 minus y over x square y equal to. So on this side, I have, what do I get? So I have the derivative of minus 1 over xy as 1 over x square y plus phi dash x, right? And when I cancel this x square y, I will have phi dash x equal to minus 1 over x square, and integrating, I just have phi x is equal to 1 over x plus some constant. And anyway, that constant will get absorbed, and I should get fxy of the form. So I was using n here, right? I had the form minus 1 over xy plus phi of x. So I would have minus 1 over xy plus phi of x equal to some suitable constant. Okay, and well, that constant, like there was a k constant mentioned there, so that c we will change later. It's just a symbol, and then we just bring all these guys up and have the same thing as minus 1 plus y equal to cxy, whatever that c or k, whatever that is. Okay, so I have this form Let me just look at the form that was mentioned there. So it talks about y, right? So let me mention this as k. Let me mention this as k, and this will be of the form y equal to 1 plus kx1. Okay. So let's look at the options that we were presented. So recall that y equal to 1 plus kxy is the solution that we have obtained. Let's go back. So f is indeed an integrating factor, but then we have these options. So whether it is k or minus k, it doesn't matter because k is in R. So 1 minus kxy and 1 plus kxy will be equivalent for this particular thing. But then the first option says this is not a general solution. So this goes out. Then y equal to minus 1 plus kxy is already out because we did that particular calculation. So this is not there. So the only correct option is the option C, right? So this particular problem actually tells you about like it is a visual trick question because the options are mentioned with alternating plus minus signs, and there will be sometimes not mentioned, sometimes not is not present, and like sometimes it is mentioned integrating factor, not integrating factor, and then there is time pressure. So this being a very easy problem, yet like it is like quite obvious that somebody could make a very stupid mistake here. So one just has to stay calm while solving this. So any issues regarding this? Eh, anything? Okay. Yes. Nothing. Okay. So let's look at a math type question. All right. So in this particular question, the m is not given, but n is given, and you just have to go ahead and find the value. So let's just go ahead. My n is 2xy. So n sub x is equal to 2y. But then this has to be equal to mx, my, right? Therefore, my mxy will have to be a function of the form y square plus c1, right? Then I have to integrate this with respect to x. So I can either do this way or go through n, but let's go through m for this one. So my f xy, which is expected to be the solution, would be of the form integral m dx, which will become xy square plus c1x plus some function of y. I take the derivatives fy equal to n to get 2xy plus 5y equal to my n function is 2xy, which tells me that phi of y is equal to 0. So y is equal to phi is equal to phi dash 1. So phi dash. equal to 0. So 5y is a constant. Put that back. My f xy became, so where was I? So there was a 2xy. Okay, wait, something has gone out. Are we missing something in one of the? So the problem has come here. I did the integration with respect to y, so this has to be a function of x. So anyway, let's keep that away. I have been given x square plus xy square is equal to c as the solution. Yeah, so we actually need to find those constants, right? So we don't need to find the constant. We only need to find M11. So this C1x, well, if this is the thing, there is actually nothing special to do, right? Fx is equal to M. So equal to, so Fx is equal to M. So I will just have 2x plus y square equal to M. That is all, right? That is actually all. Then I just have to put, this is M xy, and I will have M11 equal to 2 plus 1 equal to 3. See, so there can be situations where you don't even need to do this much of work. You can straight up take the form, find out M, be done with it. All right.
Yes, sir.
Okay. So let's talk about some integrating factors. We will try to find these out for you and take a problem on integrating factors. Okay.
Yes.
All right. So this time you have a certain differential equation given and you have certain options. All right. So let's see. So this particular equation already you can tell is not exact because there are like the first function involves degree 3 as well as degree 2 terms, and the other function only involves degree 2 terms. So overall, you are not going to get an appropriate scaling. So this is not a homogeneous one. This is clearly not an exact one. You can easily check that. You take m sub y and n sub x, these are not the same. So we will have to multiply this by something in order to make this exact. So let us look at what we had done. So if you recall, I had 1 over mu del n. Yeah. Can anyone recall the exact form? Let me just take it directly. N del m by del mu by del x, sorry, minus n del mu by del y is equal to del f by del y minus del n by del. So there are different ways you can go about. Okay, so one can clearly see that this is not exactly a function of xy or a function of y by x or something, right? Or a function of x square plus y square or some other kind of fancy function. So I believe the quickest way for solving this is actually just putting these candidate functions as your integrating factor mu and seeing what happens. Okay, so we'll just substitute the options for mu. Okay, so let's see what happens in all these cases. So mu is equal to x cube. That was the first option. So we do the multiplication and let me just write uh, m tilde equal to mu m and n tilde equal to mu n. Okay, and when I do that, let's do the multiplication and see what we get. M tilde equal to 2x cube y plus 3x x cube, right? So x power 4y plus 3x power 5y plus 6x cube y cube uh, n tilde equal to x5 plus 6x cube y square. So the thing is that a quick inspection will tell you that this is not going to be fruitful. Already in the first term, you can see m tilde y not equal to n tilde uh, x, right? Let's just evaluate it completely so that we are not making mistakes. M tilde y will be equal to 2x 4 plus 3x plus 18 x cube y square and x 5x power 4 plus 18 x square y square. Clearly, this is not working. Okay, so option A goes away, right? So what? Let me do this. Let me clear out the reasonings and just write that this doesn't work. Will that be okay? Because I want to save space. Uh, let's try. Mu is equal to y cube. Okay. So put that this is not. In this case, what are my m tilde, my tilde, n tilde, nx tilde? Okay. So x and the other one becomes x square y or 5. So here already you see there is a problem. So y is going to be 8xy plus y cube and so on. I'm not going to do this now. The thing is that already we see that there are some issues. So this particular one also does not work. right? You can actually work it yourself and see that this is not going to work. All right. Let's try out exponentials. Okay. So I will just put that exponential through each of the terms because then it will be relatively easy to evaluate the uh, respective derivatives, and also let me give these guys a space, some space. Okay. So in the first case, I'm going to get 2x y e power 3x plus 3x square y e power 3x plus 6y cube e power 3x. And here I'm getting x square e power 3x plus 6y square e power 3x. Okay. So let's look at the y derivatives. So here the exponential has nothing to do with y. So I'm going to simply get 2x e power 3x plus 3x square e power 3x plus 18y square e power 3x. On this side, I am taking n sub x. Okay, so I am going to have 3x square e power 3x plus 2x e power 3x. I am applying the chain rule, and then I have that 3 comes down 18 y square e power 3. So as you can see, I happen to get these expressions as the same, m tilde sub y and n tilde sub x, right? So this works. And like the moment it works, you really don't need to worry about why. Okay, but let's get ahead with something else.
It is also MCQ type question, no?
So this
Uh,
one was an MCQ. That is why we didn't really need to
need
do
to.
too much out of the way.
Mm.
Okay, but there are cases where something funny happens, and for that, let me get an multiple select question for you. Okay, so we have this kind of differential equation, and there are a number of questions that we need to attend. Okay, so let's see whether we can try to look at this through the lens of integrating factors, or whether we can do something else with this. Okay, so let's see. So let me just rewrite this as dy by dx equal to 2y cosec 2x plus 2 cot x. Okay. Maybe I want to keep the sign in the denominator and so on. So let me just write this in a different way. So sin x dy equal to 2y plus 2 cos x dx. Okay, then I essentially have my m xy equal to 2y plus 2 cos x and n xy equal to minus sin 2. The thing is that I will have to take this sin 2x dy on the other side to get into that form, right? So let's look at this. So let me think about this. Whether we can do this in terms of like through integrating factors, or whether we can do a simple workaround. I will also write it in a different manner. Uh, equal to 2y cosec 2x plus 2. So in case somebody wants to work in a different way. All right. So let's see how we can proceed. So again, there is this expression doesn't really look really appealing, right? Because like we won't be able to really find a mu very quickly. So let's see what we can do with this. So in the form of this, let's see what we get. So yeah, integrating factor. Uh, let's see whether we can work. No, for some reason I got disconnected. So right, people are still able to hear me, right?
Yes, sir.
Yes, sir.
Yeah. Okay, so let's see what we can do with this. Uh, let's see.
Sir,
Yes.
sir, in dy by dx form, you have written cot x. There will come na cos x
Oh,
into
yes,
cos
yes,
x.
yes. Yes, yes. So let's do that correctly. So this was not the right form. Yeah. So let's do it correctly. So wait, dy by dx. So this time let me not make a mess of this. So 2y over sine 2x plus 2 cos x over sine 2x. Okay. Now sine 2x is 2 sine x cos x. Let's simplify it in this way. And I will have y equal to sine x cos x plus 2 over sine x. Okay. This may be slightly easier to handle, I guess. I don't know. Yeah, but anyway, okay, it perhaps does help us.
2 will cancel out, na sir?
Yes, or 2 will, yeah, 2 sin x cos x, y plus cos x over sin x. Okay, so okay, in that case, we can update this a bit. So let's see. Okay, so I have y plus cos x dx minus sin x cos x dy is equal to 0. Okay. So, okay, there is a function of x and y, and then the other guy, there is only a function of n, right? So, and there is no like mixed things happening. So let us look at this. One over hold up. Hold up. This is actually, I think this can be worked in a much in a different way. So let me just take all this away. Let me write this in terms of dy by dx minus uh, y over sin x cos x. Let me keep it this way. 2x times 2 over sin 2x times 1 uh, equal to twice cos x. I will let me just convert it in this form. Why did I convert it in this form? Because I just realized that this part and this part, they happen to be functions of x alone. So this is some tx and this is qx or gx. And then such a thing can be solved using a much simpler integrating factor.
This is
Uh,
of the form of linear differential equation, right?
yes, this becomes a linear differential equation. So therefore, this can be solved in a much easier way. So so if I have this, so this is a linear differential equation, dE, and whose funda is this? If I have this in the form y dash plus pxy equal to qx, then a solution is of the form yx equal to integral e power minus integral px pt dt and qx dx. So this turns out to be the case when you have linear differential equations, right? So I think this can be solved in that way. That is far easier. Okay, let's do it. So here, this is actually minus px. So let me just take this out. So here, px is equal to minus 2 cosec 2x and qx is equal to 2 cosec. Okay, and therefore my linear equation, differential equation should have the solution y of the form integral e power uh, minus integral. So I will take that minus, cancel it here. Integral of 2 cosec 2t dt, and bottom there is 2 cosec dx. So so people can find this integral, right? The exponential integral. There is a simple substitution. I will take that 2 cos x front here. X, I have exponential. So this is of the form log cos. Wait, there is 1 over sine, right? So it is log mod. Yeah, what is it? Cosec minus cot. Okay. Yeah, whatever that is, just let me know what that is. Cos x. Let me just check this once.
It will be log mod tan x.
Log tan. Let's
Tan x.
just check. It will be log tan x.
Yes, sir.
Tan 2x. So there is a 2 here, right? It should be 2x. Just check. Yes, so it is log tan x, correct. There is a certain thing that works. So, okay, where is my pointer? Yeah, log tan x. Right, and then there is a dx. This e power log tan that will just come down and become tan x. But then this 2 cos x tan x that will convert to be twice sin x. And it just becomes minus 2 cos x plus c. Right. And I just have y pi by 4 equal to 1 minus root 2. Let's just substitute that to find out y of pi over 4 equal to 1 minus root 2. Let's just substitute that. Minus 2 cos pi over 4 equal plus c equal to 1 minus root 2. Pi by 4 is equal to 1 over root 2. So I have minus root 2 plus c equal to 1 minus root 2. It just tells you c equal to 1. And therefore the solution is yx is equal to minus 2 cos x plus 1. Okay, now let's go to the options and see what is going on. So as you can see, the function, our solution, so recall our solution is y equal to minus 2 cos x plus 1. Okay. Then one can clearly see that this function is bounded. So this first option is gone. And like it is bounded throughout, so there are no issues here. And then I will have a bounded solution as x goes to 0 and x goes to pi by 2, because this is the thing. Yes?
Yes.
Yes.
All right. Okay, cool. So actually, I okay. There is yet one last problem for the session, and then we will meet up then next Saturday. So now this is an MCQ again. And I somehow lost track of my sound. Okay. So let's have this question. I have m equal to y plus xy square. I have n equal to x minus x square y. And I have already been given mu xy is equal to x power h y power k. Right? So therefore my mu m is x power h y power k plus 1 plus x power h plus 1 y power k plus 2, and mu n is equal to x power h plus 1 y power k minus x power h plus 2 y power k plus 1. Right? So we take the respective cross derivatives. Mu m y equal to k plus 1 xhyk plus k plus 2 x h plus 1 yk plus 1. And in the second case, I will get mu n x, that is h plus 1 x h y k plus h plus 2 x h plus 1 y k plus 1. And for exactness, these have to be equal. So I should have h plus 1 is equal to k plus 1, which is the same as h plus 2 equal to k plus 2, which just turns out to be h equal to k. But then we see that this particular thing has two such options as the same, satisfying h equal to k, right? So I definitely remember this being a like single answer question, but it turns out to have two answers. And if such a thing happens, both those answers will be awarded as long as only one is selected. I think that is how it works, or like maybe later on everyone will get due credit for those. Something like that goes on.
Sir, there will be a minus in.
Yes, sir. In new
Where is the
and
minus?
X.
Yes, sir.
Oh,
Yes.
there is a
Minus of
minus.
h minus 2. Yes, sir.
Yeah, yeah,
Hmm.
yeah,
Hmm.
yeah. So then we will have to address this. So this is not going well. So I will have h plus 1 is equal to k plus 1, and I will have minus h minus 2 equal to k plus 2. Now it is just a system of linear equations, right? Right, this should be a system of linear equations now. Have I made any mistake anywhere?
No, sir. If we solve,
No,
then
sir.
we will get h equal to k equal to minus 2.
Okay. Yes, so we have gotten h equal to k from this one, and when I have h equal to k, I will have minus k minus 2 equal to k plus 2. So when I take these things, I have minus 2 to k equal to 4, k equal to minus 2, k equal to minus 2, and therefore h is also equal to minus 2. So this is right. We got the answer. Okay.
Yes, sir.
All right. So I think I have actually been able to touch upon the topics which I intended to do today. So the remaining things are, so let me just mention. So there are Bernoulli equations. So that is the only first order thing remaining, and maybe some miscellaneous ones. Some miscellaneous. These will come within first order. And then there is a real good deal about second and higher order differential equations. So differential equations with constant coefficient. Then we have method of variation of parameters. And Cauchy-Euler equations. So these are for second and higher order. Although like mostly the questions will be with second order differential equation, there may be a random surprise of having a third order or fourth order differential equation also. So there is nothing to really fear anything. We'll just see those some specific type of problems in action in the next week. All right, so now I'm open for some free questions if anyone wants to ask. This will be
Sir,
covered
is
on.
integrating factor is unique or not? So it is many.
So integrating factors are generally not unique. There are like several instances where the same differential equation can have multiple integrating factor. So let me mention one particular such instance. So so let me just mention integrating factors are generally not unique. So, for instance, we have this really simple differential equation, y dx minus x dy equal to 0. Okay. So this actually has several like different integrating factors. So let's say I can have, let's say 1 over x square. I can have 1 over y square. I can also have 1 over x square plus y square. There are more, but we will see what happens. So already, if we look at this is actually a separable equation, right? So this
Yes,
is
sir.
just dy by dx is equal to y by x, I believe, right? And this is just a bunch of lines passing through the origin, y equal to cx. You will have like log y equal to log x plus some constant, and then it will become y equal to cx in the end. So this is what you will get. Let's see what happens with the integrating factors. You should get the same answer in the end, but let's see what. So for the first one, I will have y over x square dx equal to minus 1, not minus 1 upon x dy equal to 0. So it is clear that m sub y equal to 1 over x square equal to n sub x. Okay. So this is my m, right? So let's see. Or yeah. So f equal to integral m dx, which becomes integral y over x square dx, which becomes minus y by x plus p of y. And when you take the other derivative, I will have uh, fy is equal to minus 1 over x plus y dash y. But then there is nothing else here which forces uh, phi dash y equal to 0, therefore phi y as some other constant. And that still ends up being uh, uh, so we end up having f is this, right? Minus y over x is equal to some constant. So y equal to minus c naught x. Right? You got the same thing for a different constant. You could try 1 over y square, 1 over x square, 1 plus y square, and so on, and you are still going to get a similar result. See, the thing is that this specific expression is arranged in such a way that y dx minus x dy over x square, y dx minus x dy over y square, all of these are like candidate differential forms. So even y dx minus x dy over x square plus y square, all of these are like exact differentials in one other words. So that is why these can be utilized directly. So for each of them, like there are different methods, you will get the same answer. Different integrating factors can exist. Any other questions?
Sir, in general case, we can always get such non-unique integrating factor or
So like that uniqueness is not there typically there. You can have different ways, but of course some ways can be way too unwieldy. Sometimes you will get an easier answer. So that easier answer is possible when you can see, the idea is you somehow have to obtain a relatively easy looking form, which can be converted into an exact differential.
yes.
Yeah, so there can be different ways of approaching that. So like each way will correspond to a different integrating factor. But in like complicated cases, like only one is needed, right? In the end, you only need to find a solution. Of course, that
Yeah.
only is too broad a word, because you will get like finding that can be tedious.
Okay, sir.
Any more questions?
Sure.
I hope there are no more queries left. Thank you so much for such an engaging and wonderful session, Gaurav sir.
Yes,
So,
thank you
but
very much, sir.
yeah, welcome, sir.